What specific problem does the Real-TabPFN method aim to solve, and why is it significant in the context of tabular prediction tasks?
The Real-TabPFN method aims to enhance the in-context learning performance of the TabPFN v2 model by continuing its pre-training on a carefully curated set of real-world datasets from OpenML and Kaggle. This is significant because traditional tree-based algorithms have historically outperformed neural networks on tabular prediction tasks, and while TabPFN v2 has shown improved performance on small datasets, it is not universally superior. By integrating real-world data into the pre-training process, Real-TabPFN addresses the limitations of relying solely on synthetic data, thereby improving generalization and adaptability across diverse tabular problems. The empirical results demonstrate that Real-TabPFN consistently outperforms its predecessor on 29 small tabular datasets, indicating its potential to provide more accurate predictions in critical domains like healthcare and finance. This advancement opens new research directions in leveraging real-world data for tabular foundation models, which is crucial for achieving better outcomes in practical applications.
How does the proposed method of continued pre-training work? Illustrate it step by step, including the roles of both synthetic and real-world data in the two-stage approach.
The proposed method of continued pre-training employs a two-stage approach to enhance the TabPFN v2 model. In Stage 1, the process begins with the original TabPFN v2 checkpoint, which has been pre-trained on a large and diverse set of synthetic tables, serving as a robust foundation. Stage 2 involves continued pre-training exclusively on a curated collection of heterogeneous real-world tables sourced from OpenML and Kaggle, which helps improve generalization and adaptability. This method contrasts with mixed training, as it avoids simultaneous feeding of synthetic and real samples, allowing the model to build on its strong synthetic base without interference. The combination of synthetic data in Stage 1 and real-world data in Stage 2 leverages the strengths of both paradigms, ultimately leading to improved in-context learning performance, as evidenced by the significant accuracy gains observed in the Real-TabPFN model.
Can you provide a simple yet illustrative example of how the Real-TabPFN algorithm operates during continued pre-training and in-context learning? Walk through the process using a hypothetical dataset.
The Real-TabPFN algorithm operates through a two-stage continued pre-training process, starting with the original TabPFN v2 model, which has been pre-trained on synthetic data. For example, consider a hypothetical dataset containing 15,000 samples and 20 features related to customer transactions. In Stage 1, Real-TabPFN begins with the pre-trained weights from TabPFN v2 and then enters Stage 2, where it continues pre-training exclusively on this real-world dataset. During this stage, the model processes the dataset in batches of one, allowing it to utilize the full context of the 15,000 samples without padding. The training objective incorporates a regularization term that penalizes deviations from the initial weights, ensuring stability and mitigating catastrophic forgetting. After this continued pre-training, the model can then be evaluated on unseen data, leveraging its enhanced in-context learning capabilities to make accurate predictions based on the patterns learned from the real-world dataset.
What are the theoretical or practical benefits of using Real-TabPFN over its predecessor TabPFN v2, particularly in terms of performance on small datasets?
Theoretical and practical benefits of using Real-TabPFN over TabPFN v2 include its superior in-context learning performance, as evidenced by consistent outperformance on 29 small tabular datasets. Real-TabPFN achieves a mean normalized ROC-AUC improvement from 0.954 to 0.976, indicating enhanced predictive accuracy. This improvement is attributed to the model's continued pre-training on a carefully curated set of real-world datasets from OpenML and Kaggle, which provides complementary supervision signals that synthetic data alone cannot offer. Additionally, the two-stage pre-training approach allows Real-TabPFN to leverage the strengths of both synthetic and real data, enhancing generalization and adaptability across diverse tabular problems. Overall, Real-TabPFN serves as a stronger off-the-shelf baseline for tabular classification tasks compared to TabPFN v2.
How is the effectiveness of Real-TabPFN validated? Discuss the experimental design, datasets used, and metrics for performance evaluation.
The effectiveness of Real-TabPFN is validated through a rigorous experimental design that employs 10-fold cross-validation on 29 small tabular datasets from the OpenML AutoML Benchmark, ensuring a robust evaluation framework. The datasets, which contain up to 10,000 samples and 500 features, were carefully curated to avoid data contamination, with a multi-tiered filtering process implemented to ensure no overlap with the training data. Performance evaluation metrics include the mean normalized ROCAUC, where Real-TabPFN significantly improved from 0.954 to 0.976 compared to its predecessor, TabPFN v2. Additionally, the model's performance was compared against various baselines, demonstrating that Real-TabPFN consistently outperforms them on average. The experiments also included an analysis of the impact of different training data sources, confirming that the combination of OpenML and Kaggle datasets yields the best performance, further validating the model's effectiveness.
What specific results were achieved with Real-TabPFN compared to TabPFN v2? And what do these results indicate about its performance on various datasets?
Real-TabPFN significantly outperformed TabPFN v2 across 29 small tabular datasets, as evidenced by an increase in the mean normalized ROCAUC from 0.954 to 0.976. This improvement indicates that Real-TabPFN not only enhances in-context learning performance, but also serves as a stronger off-the-shelf baseline for tabular classification tasks. The results demonstrate that the continued pre-training on real-world datasets effectively boosts the model's generalization capabilities, allowing it to better handle diverse tabular data. Additionally, the combination of datasets from OpenML and Kaggle yielded the best performance, suggesting that heterogeneous data sources provide complementary supervision signals that further enhance model accuracy. Overall, these findings highlight Real-TabPFN's superior adaptability and effectiveness in various tabular prediction scenarios compared to its predecessor.